Something hit Earth last week, and most people had absolutely no idea it was coming. Not an asteroid, not a missile, not anything you could see with your eyes or feel under your feet. What hit us was invisible. It travelled at 1,000,000 miles an hour, and it came from 93 million miles away. It came from the sun, and when it arrived it lit up the sky over France. It painted green curtains of light over New Zealand. It made the magnetic field of our entire planet shudder, like a bell that had just been struck by something enormous. People who had never seen the northern lights in their lives walked outside on a Monday evening and stood there with their mouths open, looking up at something they did not expect to see above their city. This is the story of that storm, where it came from, what it actually did, what it could have done, and what it means for you right now in the weeks ahead. Because the sun is not done, not even close. Let's start at the beginning. Not the beginning of the storm itself, but the beginning of the week that made it possible. Because what hit Earth on June 8, 2026 did not come out of nowhere. It was the product of one of the most restless, most active stretches of solar behavior we had seen in months. And to understand why it hit so hard, you need to understand something that sounds almost mundane when you first hear it. 2 clouds of solar material were already on their way to us, and a third one caught up to them. We'll get to that. But first, let's talk about the sun itself. Because I think most of us, most of the time, treat the sun the way we treat the floor beneath our feet. It's just there, it's reliable, it rises, it sets, it keeps us warm. We don't think about it much. And that is a reasonable way to feel, because for most of human history, the sun was exactly that, a constant, a given, a background feature of life on Earth. But the sun is not a constant, it is an engine. A roiling, churning, magnetic engine about 1,000,000 times the volume of Earth, made entirely of plasma, which is essentially superheated gas where the atoms have been torn apart, and their electrons are flying free. And like any engine running hot for billions of years, it is not always smooth. It surges, it spits. It occasionally releases more energy in a few minutes than the entire human civilization has consumed in all of recorded history. The way the sun releases that energy is through sunspots. Now, sunspots have a reputation for being dull. They show up in high school physics textbooks as small dark patches on the solar surface, something to do with magnetism. Moving on, next chapter. But here is what a sunspot actually is and why it matters enormously. Deep inside the sun, magnetic field lines are constantly moving, being dragged around by the churning plasma, getting tangled and twisted over days and weeks. Sometimes, a bundle of those twisted field lines pushes up through the surface and emerges into the outer atmosphere. Where those field lines poke through, the normal flow of heat from below is disrupted, so that patch of the surface runs cooler than the surrounding area. Cooler means darker. That is the sunspot. But the visible dark patch is almost beside the point. What matters is the stored magnetic energy in those twisted field lines, because when field lines of opposite polarity get pushed too close together, they eventually snap, they reconnect, and when they do, the energy that was stored in that magnetic tension is released all at once, explosively, in a burst that sends light and radiation racing across the solar system at the speed of light, reaching Earth in 8 minutes. That is a solar flare, and sometimes, not always, but in the biggest events, almost always, the flare is accompanied by something even more significant. The explosion rips open the outer atmosphere of the sun and hurls a massive cloud of superheated plasma out into space. Billions of tons of it. A cloud so large it would dwarf the Earth the way a house dwarfs a marble, moving at anywhere from 500 to 2,000 kilometers per second or more. That cloud is what scientists call a coronal mass ejection, and it is heading our way. Now, the week of June 3, 2026 started with a sunspot that had been growing more complex for several days. The sunspot region was called AR4455, Active Region 4455, and it was sitting almost dead center on the sun's face as seen from Earth. That positioning matters. When a sunspot sits at the center of the solar disk, any eruption it produces is almost perfectly aimed at us. The geometry is simple. You are standing on Earth, the sun is in front of you, the sunspot is at the center of the sun's face. When it fires straight at you, and AR455 fired. 3 times in under 24 hours at 01:22 in the morning. Universal time on June 3, the region produced a flare. A big one, measuring M93, which is near the top of the second highest category of solar flare. The M category sits just below the X category, which is the highest tier, and M9.3 is right at the doorstep of the most powerful class of eruption the sun produces. The flare lasted about 20 minutes, flooding the solar system with X-rays and ultraviolet radiation, and it launched a cloud of plasma that space weather physicist Dr. Tamitha Skov confirmed was heading directly toward Earth. Then, not even 6 hours later, the same sunspot fired again. An M77 flare at universal time, another large eruption, another cloud of plasma heading our way. And then at 11:28 that same morning, AR4455 crossed a threshold. It produced an X-class flare, highest category, an X 1.0. 3 major eruptions from a single sunspot in under 11 hours, all of them aimed at Earth. When Dr. Skov posted about the M93 and M7.7, she said something that should have caught everyone's attention. She said, essentially, that since this was the second significant eruption from the same region in a short time, the second cloud might get held up in traffic on its way to Earth. That phrase, held up in traffic, sounds casual, but it was describing something very real and very important. The first cloud was already on its way out, the second cloud was faster. And when a faster cloud of solar plasma catches a slower one in the space between the Sun and Earth, something happens that changes everything about how that storm eventually hits us. But before we get there, let's talk for a moment about why these solar storms affect Earth at all. Because it's not obvious, and I think a lot of people have a vague sense of solar flares are bad without really understanding the mechanism. The key is Earth's magnetic field. Our planet is surrounded by an invisible magnetic bubble that extends tens of thousands of kilometers out into space in every direction. You can think of it as a kind of shield. Under normal circumstances, the stream of particles and magnetic energy constantly flowing outward from the Sun, what scientists call the solar wind, hits this bubble and flows around it, the way a river flows around a large rock. The interior of the bubble where Earth sits stays relatively calm. That's the default state. That's what things look like on a normal day, but the solar wind carries its own magnetic field embedded in it, and most of the time, that field is oriented in a direction that doesn't couple strongly with Earth's magnetic field. They don't connect, they just slide past each other. The bubble stays intact now. When a massive solar storm cloud arrives, it brings with it a much stronger magnetic field than the ordinary solar wind. And here is the thing that determines everything about how bad the resulting storm will be: the direction of that magnetic field. Specifically, whether the field in the incoming cloud is pointing north or south. If it points north, it aligns with Earth's own field, the two fields sit comfortably next to each other, and the storm is muted. If it points south, it points in the opposite direction to Earth's field, and when two magnetic fields of opposite orientation are pushed together, they don't just sit there, they reconnect. They essentially merge and reorganize, and in doing so they open a gateway. Solar energy pours through that gateway into the space around Earth. Energetic particles, protons and electrons, are funneled down along Earth's magnetic field lines toward the poles, and when those particles collide with the air in the upper atmosphere, at altitudes of roughly 100 to 400 kilometers up, they excite the atoms of oxygen and nitrogen in the air, and those atoms release that energy as light. That is the aurora, the northern lights, the southern lights. That is what it actually is: solar particles colliding with air 100 kilometers up, in a ring around the poles, producing curtains and ribbons of green and red and violet light. The stronger the storm, the more energy pours in, and the further from the poles that glowing ring expands. On a typical night, you need to be in northern Norway, or northern Canada, or Iceland, or Antarctica to see it. During a moderate storm, you might see it from Scotland or Minnesota. During a major storm, you might see it from France. During the most extreme storms, the kind that have only happened a handful of times in the last few centuries, the aurora has been seen from the Caribbean, from Southeast Asia, from the tropics, and nobody, not a single space weather scientist on the planet, knows for certain whether the incoming cloud's magnetic field will point north or south until that cloud is almost on our doorstep, until it passes the monitoring satellites that sit about 1 million miles in front of Earth, in a gravitational balance point called L1. Those satellites measure the field in real time and radio the data back to Earth. The trip from L1 to Earth takes about 45 minutes. That is your warning window. 45 minutes between this storm is going to be severe and the storm is here. 45 minutes for grid operators to take protective action, for airline dispatchers to reroute polar flights, for satellite controllers to put their spacecraft into safe mode. It sounds like a very short window, and it is, but it is infinitely better than no warning at all, which is what humanity had for most of its history. And it is something that the people at NOAA's Space Weather Prediction Center work around the clock to maximize, so that when a storm arrives, the downstream systems have every possible second to respond. Now, back to June 2026. By June 5th, the CMEs from the June 3 eruption sequence had arrived and stirred up some activity, but not at the G4 severe level some forecasters had thought was possible. The storm was real but manageable, and then on June 6, the solar disk produced its next move, a sunspot called AR4461. A different one, not the hyperactive AR455, fired a flare at 14:01 Universal Time. It was a moderate flare, the kind that earns a brief mention in a NOAA bulletin on a slow day. Not dramatic, not alarming on its own, but it launched a cloud of plasma out into space, and that cloud was moving faster than what was already out there between the Sun and Earth. The leftovers, the slower material from the earlier eruptions of June 3. The faster cloud began catching up to the slower one, and here is where things get genuinely unsettling. When a faster solar storm cloud catches a slower one in transit, they don't just add together. The faster cloud plows into the slower one. It compresses it, sweeps it up, merges with it. The resulting merge structure is denser than either cloud on its own. It carries more total magnetic energy than either cloud on its own, and its internal magnetic field, that crucial north or south orientation that determines storm strength, becomes a chaotic tangle of two different flux ropes merged together. Scientists call this kind of event a cannibal CME, because the faster cloud effectively consumes the slower one. And the thing about a cannibal CME is that it is far harder to forecast than a normal one, because the merged magnetic structure is scrambled in a way that the models can't fully predict. Even the best computer simulations of solar storm propagation cannot tell you with confidence which way the magnetic field of a cannibal CME will be pointing when it arrives. You won't know until it gets to L1. NOAA knew this. On the evening of June 6 at 22:11 Universal Time, they issued a watch for a strong geomagnetic storm, what they call a G3, expected to arrive on June 8. And instead of giving a single expected storm level, they gave a range. They said the storm could reach anywhere from G1 to G3, with G3 being the threshold they were planning around, but G4, severe, being within the realm of possibility depending on how the magnetic field aligned when it arrived. That range of uncertainty, rather than a single confident prediction, was the honest, scientifically rigorous acknowledgement that a cannibal CME had just made the forecast significantly harder. Around this same time, the GOES-18 satellite, one of the weather satellites America keeps in orbit to monitor the space environment near Earth, was already recording elevated levels of high-energy electrons. On June 7 at 11:43 Universal Time, the electron flux exceeded the alarm threshold. By the following day, the 24-hour maximum was nearly 3 times the alarm level. These high-energy electrons don't cause aurora. They don't trip grid relays. What they do is slowly, invisibly work their way through the outer shielding of satellites and build up charge inside the electronics. When that charge discharges suddenly, it can damage circuits, scramble memory, or trigger unexpected commands in spacecraft. It's the space weather equivalent of static electricity, except the bolt you don't see is frying a component worth millions of dollars on a satellite worth hundreds of millions of dollars, moving at 7 kilometers per second, 500 kilometers above your head. June 8, 2026, Monday. The storm arrived, the shock front hit Earth's magnetosphere, and the KP index, the global measure of geomagnetic disturbance running on a scale from 0 to 9, climbed to 7. That is the G3 level. Strong. And what happened next was both beautiful and, to anyone paying attention to what it implied, a little bit frightening. The Aurora expanded. The oval of glowing light that normally sits above the Arctic and Antarctic widened, pushed down toward the equator by the intensity of the energy pouring into Earth's magnetosphere. In northern France, people who had never seen the northern lights in their lives, people for whom a glimpse of Aurora was something that happened only to the very lucky or the very far north, walked outside and found the sky rippling with green and pink light. In Christchurch, New Zealand, a city in the southern hemisphere at roughly the latitude of Paris in the north, the southern lights were photographed dancing above the houses. In Adelaide, Australia, in Edinburgh, Scotland, which went absolutely wild on social media, in Copenhagen, in Seattle, Washington. An aurora photographed from Seattle means that the storm was strong enough to push the visible edge of the light show to about 47 degrees latitude. That is not something that happens on a quiet Tuesday. That is a planet whose magnetic field is being actively worked over by something large that came from the sun. And here is the thing that matters alongside the beauty. The KP index hit 7 and the aurora lit up France. But the infrastructure largely held. As of Tuesday morning, June 9, no confirmed major infrastructure failures had been publicly reported. The power grid kept running, the GPS satellites kept broadcasting, planes kept flying, and this might tempt you to think, well then what's the big deal? The lights were pretty, the satellites survived, the grid didn't go down. Where's the actual danger? The danger is not in the G3 storm that happened. The danger is in understanding what a G3 storm is telling you about the sun, and more importantly, what it is telling you about what a G4 or G5 storm would do, which is something that is not merely theoretical. Let's talk about what actually happens inside a power grid during a geomagnetic storm, because I think this is one of those things that sounds abstract until you understand the mechanism. When Earth's magnetic field is being disturbed by a solar storm, The disturbance creates slow variations in the magnetic field at ground level, and because of the way electromagnetism works, the relationship between a changing magnetic field and electric current that Faraday worked out almost 2 centuries ago, those variations drive actual electrical currents in any long conducting structure that runs across the ground. Long power lines, natural gas pipelines, submarine cables, railway lines, these all act as unintended antennas for the electrical effects of the storm. The transformers at the ends of those power lines were designed to handle alternating current that oscillates back and forth 60 times per second. What the storm drives into them is not oscillating current. It is a slow, almost steady current in one direction, and transformers respond very badly to this kind of current. They begin to saturate magnetically, they run hot, they pull extra reactive power from the grid around them, which causes the local voltage to drop. Protective relays sense the anomaly and trip the line, and if enough lines trip in a short period, the grid, which is a system that requires a precise balance of supply and demand at all times, can cascade into failure, not because the storm destroyed anything in a dramatic cinematic way, because it quietly pushed dozens of components just past the edge of their operating limits, in a cascade that the operators couldn't stop fast enough. This is exactly what happened in Quebec, Canada, on March 13, 1989. That night, a solar storm hit Earth, not a G3, but a full G5 extreme event, and the Hydro-Quebec power grid collapsed in under 2 minutes. 6 million people lost electricity. It was not the middle of a heat wave or a cold snap. It happened to be a cool spring night which probably saved lives, because the temperatures were tolerable without heat or air conditioning. But the province was dark for 9 hours. Power transformers in New Jersey overheated, communications were disrupted, and a key detail that is worth sitting with, this storm, the one that knocked out Quebec in 1989, was not even close to the strongest storm in the historical record. It was severe, it was damaging. But the storms that have hit Earth in the past, over the centuries and millennia, have been far, far stronger. The most extreme solar storm in recorded history happened on September 1 and 2, 1859, and it has a name, the Carrington event, named after the British astronomer Richard Carrington, who happened to be at his private observatory outside London, carefully drawing a group of sunspots, when he observed something that no human being had ever consciously witnessed before. 2 intensely bright patches of white light erupted from within the sunspot group and faded within 5 minutes. He was watching a solar flare in progress. Within 18 hours of that observation, a solar storm hit Earth that remains to this day the most powerful geomagnetic storm in documented history. The effects were extraordinary and, seen from a modern perspective, terrifying. The aurora was visible across the tropics, not just in Scotland or France, in Cuba, in Colombia, in Hawaii, in parts of what is now Vietnam and Japan. People reportedly woke in the middle of the night believing it was dawn. The sky was so bright with the southern lights. The telegraph systems across the United States and Europe, which were the internet of their day, the entire global communication backbone, failed, sparked, and in some cases caught fire. The geomagnetically induced currents were strong enough to ignite paper in telegraph offices. Some operators reported receiving electric shocks from their equipment, and in a detail that passes into legend, some telegraph operators reported being able to continue sending and receiving messages even after they had disconnected their batteries, because the storm itself was pushing enough current through the lines to operate the equipment. The solar storm was powering the communication network of the planet. In 1859, that was alarming but ultimately not civilization-threatening, because civilization in 1859 ran on coal and steam and horse and muscle. The electric grid did not exist. Sensitive electronic components did not exist. Satellites did not exist. The most vulnerable technology was the telegraph, and the telegraph, for all its importance, could be replaced relatively quickly. Today, the calculation is completely different. A storm of Carrington intensity arriving in the current era would interact with a civilization that depends on the power grid for essentially everything: hospitals, water treatment, communications, financial transactions, internet, food refrigeration, fuel pumps. The supply chain that keeps grocery store shelves stocked, all of it runs on electricity. And the components most vulnerable to a major geomagnetic storm, the massive custom-built transformers that step electricity up to high voltage for long-distance transmission and back down for local distribution, cannot be quickly replaced. They are not mass-produced items sitting in a warehouse. They are built to order, they weigh hundreds of tons each, and they take between 5 and 16 months to manufacture and ship. In a severe storm that damaged a significant fraction of those transformers in a major grid region, restoring power would not be measured in hours, it would be measured in months. A risk model commissioned by Lloyd's of London estimated that a Carrington-class storm hitting the United States today could cause between $600 billion and $2.5 trillion in economic damage. The UK's Science and Technology Facilities Council published a report in January 2026, specifically designed to help governments and infrastructure operators plan for a worst-case space weather scenario. The report does not present this as science fiction or remote speculation. It presents it as a low probability but real and plannable risk, the same category of thinking as planning for a major earthquake in a seismically active city. You don't know exactly when, but you know the physics, you know the historical record, and you know that the physics has not changed. The 1989 Quebec storm, which was far less intense than the Carrington event, collapsed a major power grid in under 2 minutes. The May 2024 storm, which you may remember, which reached G5 for a sustained period and put Aurora over Florida and Texas, did not collapse any grids, but it caused enough disruption to GPS signals that the American agricultural sector, which depends heavily on GPS for precision farming, automated planting, harvesting and soil management, estimated losses of around $500 million from that single event. $500 million from one storm, from a technology disruption that most people didn't even notice, because they were too busy taking photos of the Aurora. Now think about that for a moment, from the perspective of Southeast Asia, from Vietnam specifically, because this is something that doesn't get talked about enough in the space weather conversation. The popular narrative around solar storms focuses heavily on the Aurora, the beautiful light show, and on the vulnerability of high-latitude power grids, because geomagnetically induced currents in the ground are strongest at high latitudes near the poles, where Earth's magnetic field is oriented steeply downward and the geometry of the disturbance is most intense. And that is accurate. Quebec is more vulnerable than Madrid, Stockholm is more vulnerable than Singapore, but GPS disruption is a different story. GPS disruption during geomagnetic storms is actually most severe not at high latitudes, but near the equator. This surprises people. Here is why it happens. The disturbance from a solar storm doesn't just affect the air near the poles, it disturbs the entire global electrical environment of the upper atmosphere, the ionosphere, the layer of ionized air between about 60 and 1,000 kilometers altitude that your GPS signal travels through on its way from the satellite to your phone. Near the equator, this ionosphere responds to geomagnetic storms by developing turbulent pockets of irregular density, bubbles and plumes of ionization that scatter and delay the GPS signal in unpredictable ways. The result is that your GPS receiver cannot confidently calculate its position because the signal has been bent and slowed by these invisible atmospheric irregularities. The positioning error can jump from the usual meter or two to tens of meters, without warning, without your device showing anything unusual on the screen. Vietnam sits between roughly 8 and 23 degrees north of the equator, right in the heart of the equatorial zone where this effect is most pronounced. And Vietnam's economy, like so many economies in Southeast Asia, is increasingly dependent on GPS-linked systems, precision agriculture in the Mekong Delta, maritime navigation in the South China Sea, urban traffic management, drone delivery logistics, mobile payment systems and 5G networks, which use GPS timing signals to synchronize their base stations. These systems assume GPS is reliable. During a G3 or stronger geomagnetic storm, it isn't, and that unreliability doesn't announce itself loudly. A delivery drone may drift from its path by 30 meters and land in the wrong place. A fishing boat may have its chart plotter showing an incorrect position. A precision planting machine may lay seed rows that are off by enough to interfere with the efficiency the system was supposed to deliver. None of these individual failures are catastrophic, but multiply them across millions of devices, across a region of 600 million people, over the course of a storm that lasts 12 to 36 hours, and the economic disruption adds up in ways that never get attributed to the solar storm, because most people don't know to look. Let's come back to the present. As of June 10, 2026, the G3 storm from June 8 is winding down. The residual effects, slightly elevated geomagnetic activity, some lingering disruption to the upper atmosphere, are fading, but the sun is far from quiet. The face of our star that is currently turned toward Earth holds 7 numbered active sunspot regions, and among them at least 2 are carrying magnetic configurations that space weather forecasters watch very carefully. AR4456 is classified at the highest tier of magnetic complexity. What that means in plain language is that within a single sunspot group, regions of opposite magnetic polarity are pushed so close together, essentially touching, separated by a distance smaller than what you'd see between 2 average sunspots in a normal group, that a powerful flare can erupt with almost no warning. These highly complex sunspots are the ones that produce the sudden X-class events that arrive before forecasters have had time to fully characterize the eruption and update their alerts. NOAA was giving the current disk configuration a 55% chance of at least one significant M-class flare and a 10% chance of an X-class event through June 10. That 10% number sounds modest, but if you rolled a 10-sided die every day, landing on one specific number, you'd hit it about 36 times in a year. The sun rolls that die every day. Some weeks it comes up. A second sunspot, AR4464, developed an even more complex magnetic configuration during the June 8 and 9 period and has moved to the top of the watch list. And a brand new sunspot, AR4465, rotated into view over the edge of the solar disk to replace departing AR4455, which has finally rotated past the western edge of the sun after its extraordinary week of activity. The cast is changing, the drama is not, and there is one more piece of the near-term picture. Around June 11, Earth is expected to encounter the fast solar wind streaming outward from a large dark region on the sun's surface called a coronal hole. Unlike sunspots, which are magnetically complex and prone to explosive eruptions, coronal holes are more like open windows, regions where the sun's magnetic field doesn't loop back on itself but instead points outward into space, allowing fast solar wind to stream continuously in that direction. When Earth rotates into the path of one of those streams, the result is typically a prolonged but lower intensity period of geomagnetic activity. Not dramatic, not Aurora over France levels, but enough to keep the upper atmosphere and the space environment around Earth slightly stirred up for 2 to 3 days. On a quiet sun, that's a minor event. Coming on the heels of the week that just happened, it means the recovery is going to be interrupted. Grid operators at high latitudes, satellite controllers, and airline dispatchers will be monitoring for elevated conditions again by the middle of the week. Now let's zoom out, because all of this, the cannibal CME, the G3 storm, the auroras over France and New Zealand, the complex sunspots still loading on the solar disk, needs to be understood in the context of where we are in the sun's natural cycle. The sun does not produce the same amount of activity all the time. It goes through an 11-year cycle, from quiet to active and back to quiet again. At solar minimum, the disk is often completely blank for days or weeks. Sunspot counts hover near zero. Major flares are rare. Geomagnetic storms above G1 are uncommon. At solar maximum, the disk is loaded with sunspot group. Major flares happen multiple times a week, and significant geomagnetic storms become a near-monthly occurrence. Solar cycle 25. The current cycle, which began in December 2019 when the previous minimum was reached, officially hit its maximum in October 2024. The peak was earlier and stronger than the international panel of scientists that monitors the solar cycle had predicted. They had expected the peak in July 2025, with a sunspot number around 115. The actual peak arrived months ahead of schedule and exceeded what had been forecast. The sun surprised everyone by being more active than the models predicted. That alone is worth noting, because it means the models are not perfect, and the sun does not consult our projections before deciding what to do. We are now on the declining slope past that October 2024 maximum. Sunspot activity has generally been trending downward since February 2026, when the Solar Terrestrial Activity Report noted a strong decrease in observed sunspot numbers. But, and this is important, declining does not mean quiet. The slope from solar maximum to solar minimum takes years to traverse. Cycle 25 began in December 2019 and is expected to last until roughly late 2030 or 2031, when the next minimum arrives. That means we are roughly in the middle of the cycle in terms of time elapsed, but on the downhill side of the activity peak, and downhill, in solar cycle terms, still means years of elevated activity compared to the quiet years at the bottom. Active region AR4455, which fired 3 major eruptions in a single day on June 3, 2026, is proof that the sun is still very much capable of producing the kind of week we just had. The cycle is declining. The sun is still very much alive. Space weather researchers have specifically called out the period from early 2026 through mid-2027 as a window of sustained, elevated risk for satellite infrastructure and for high-latitude power grids. Not because a catastrophic storm is inevitable during that window. It isn't, and the base rate of truly extreme events is low, but because the solar disk will continue producing complex sunspots and CMEs at a rate significantly above what it does at solar minimum, and the cumulative exposure to moderate storms during an elevated period carries real operational consequences for the industries that depend on a stable space environment. Which brings us to the question of what you can actually do about any of this. And here I want to be very direct with you, because there is a version of the space weather conversation that tips into alarm and doomsday framing that I think is both inaccurate and unhelpful. Let me be clear about what is true and what is not what is true. Geomagnetic storms of G3 and above, like the one that hit on June 8, are real events with real consequences for infrastructure. They happen multiple times per year during solar maximum conditions. The vast majority of those consequences are managed by the professionals who operate grids, satellite systems, and aviation, and they do so competently using the forecasts and alerts that NOAA and other agencies provide. The June 8 storm produced beautiful auroras and, as far as publicly available reporting shows, no significant infrastructure failures. That is the expected outcome for a well-managed G3 event. What is also true, the risk is not zero. The history of geomagnetic storms includes the Quebec blackout of 1989, which was a real and serious event. The history includes the 2024 G5 storm and its documented economic effects on GPS-dependent agriculture. The history includes the Carrington event of 1859, which is a real benchmark that scientists use to define worst-case planning scenarios. The January 2026 UK report that laid out worst-case environments was not written to frighten people. It was written to inform planning so that grid operators, satellite builders, and governments have a scientifically grounded sense of what they need to be hardened against. What is not true? The idea that you should be stockpiling supplies, building a Faraday cage for your house, or living in fear of the next solar storm. The risk is real, but it is manageable, and the vast majority of it is managed by systems and people you will never interact with directly. What is appropriate is awareness, knowing that these events happen, following NOAA's Space Weather Prediction Center if you work in an industry that's affected. Agriculture, aviation, maritime, energy, telecommunications. Knowing that during a major storm watch, the aurora might be visible even from low-latitude locations, and that your GPS might be slightly less reliable, and that HF radio communications might be degraded. That's not a crisis. That's background knowledge for a world where the sun is actively involved in our technological environment. The monitoring architecture that gave us the June 8 warning, NOAA's G3 watch issued 36 hours before the storm arrived, the real-time measurements from the L1 monitoring satellites, the WSA-NLIL computer model that predicted the arrival time with remarkable accuracy, represents decades of investment in space weather science and operations. It is genuinely impressive, and it saved real money on June 8 by allowing grid operators and satellite operators to take precautionary action before the storm hit, rather than scrambling to recover after it. But that architecture has vulnerabilities. The DISCO VR spacecraft sitting at L1, measuring the incoming solar wind in real time and providing that crucial 45-minute warning, is aging. It was launched in 2015. It is running past its planned mission line, thus no immediate replacement in place. If DISCO VR fails, the warning window shrinks dramatically to roughly 15 minutes based on ground-based measurements, not enough time to execute the protective actions that the longer warning allows. The scientific community and the space weather operations community have been raising this gap for years. It is the kind of infrastructure vulnerability that tends not to get funded until the day it becomes an emergency. Let's hope it gets funded before that day. There is one more thing I want to talk about before we close. Something that lives in the more speculative territory of space science, that the mainstream research community does not accept as established, but that a small number of independent researchers find interesting enough to keep investigating. And I want to be completely honest with you that this is speculation, not science, something to be aware of as a hypothesis, not something to act on as a conclusion. The idea is this. Some researchers have noticed that in the days following major solar events, large flares, significant CME arrivals, there are statistical patterns in earthquake catalogues that they believe are more than coincidence. The hypothesis is that the energetic particles arriving with a solar storm and the associated changes in Earth's electrical environment might influence the behavior of already stressed geological fault systems, not cause earthquakes from scratch, not even necessarily trigger specific quakes with certainty, but perhaps nudge the timing of ruptures at faults that were already close to the breaking point. The mechanism that most often gets proposed involves the ionosphere. The theory suggests that rapid changes in the ionosphere during a geomagnetic storm could create very low-frequency electromagnetic signals that penetrate the Earth's crust and alter the electrical environment around the water and fluids that play a role in fault friction. Some researchers have pointed to correlations between major geomagnetic storms and increases in seismic activity in the following days. Some seismological data centers have papers in their archives exploring this. But, and I want to say this clearly, mainstream seismology does not accept this hypothesis. USGS earthquake probability models do not include solar activity as a variable. The correlational evidence that exists is contested, with equally credible researchers looking at the same data and finding no statistically significant pattern above what you'd expect from chance. This is a question that is genuinely unresolved at the edges of science, not a conclusion that responsible scientific consensus has reached. Sit with it as an interesting thought. Don't build an earthquake preparedness plan around it. The real preparedness message for earthquake risk remains what it has always been. Understand the fault systems near where you live, know what to do when shaking begins, and keep a basic emergency kit at home. The reason I mention it at all is because I think it represents something genuinely valuable about how to engage with natural phenomena like solar storms. They are not isolated events happening in a vacuum in space, disconnected from life on Earth. They interact with our technological systems. They interact with our upper atmosphere in ways that have downstream effects on communications, navigation, and climate at the margins. And researchers at the edges of various fields are genuinely asking whether they interact with geological systems in ways we don't yet fully understand. Most of those hypotheses will turn out to be wrong. A few, historically, have turned out to be right in ways nobody expected. Science makes progress precisely by taking those edge ideas seriously enough to test them rigorously, while being honest about what the testing has and hasn't shown. What we can say without any uncertainty, looking back at the week of June 3 through 10, 2026, is this. The Sun fired 3 major eruptions from a single sunspot in under a day. It launched a cannibal CME, a merged storm cloud that is harder to forecast than a normal one toward Earth. That cloud arrived 2 days later, pushed Earth's magnetic field hard enough to light up the sky over France and New Zealand, elevated the space radiation environment around our planet, and produced effects on satellite electronics and GPS accuracy that were real, even if invisible to most people on the ground. All of this happened not during the most active phase of the solar cycle, but on the declining slope past the peak, during a period that space weather researchers describe as one of sustained elevated risk that will continue through at least mid-2027. And as of this moment, June 10, 2026, the Sun's face still holds sunspot regions of extraordinary magnetic complexity, with a meaningful probability of producing additional major flares in the coming days. A fresh stream of fast solar wind from a coronal hole is arriving around June 11. The stage is set for continued activity. This is not a story about catastrophe. It is not a story about the end of civilization or a planet-killing solar superstorm descending upon us. The professionals at NOAA's Space Weather Prediction Centre, at NASA, at ESA's Space Weather Service Network, at the UK Met Office Space Weather Operations Centre, and at national space weather centres around the world, are watching, modelling, forecasting and alerting every hour of every day. They are genuinely good at their jobs. The monitoring system is genuinely impressive. The forecast for the June 8 storm was issued 36 hours in advance, was accurate to within hours of arrival time, and the storm was managed without a single confirmed major infrastructure failure. But the monitoring system is also finite. It depends on aging spacecraft that need to be replaced. It depends on budget allocations in an era when funding for scientific infrastructure is constantly under pressure. It depends on a world where the people who operate the vulnerable infrastructure, the grid, the satellites, the aviation system, are paying attention to the alerts and have both the authority and the procedures to act on them within the window they're given. The June 8 storm was a moderate event by the historical scale of what the Sun is capable of producing. It was a G3. The Quebec storm was a G5. The Carrington event was something we don't even have a modern G-scale number for, because the instruments that would measure it didn't exist in 1859. The gap between a G3 and a Carrington-class event is not a small step. It is enormous. But the direction of where that gap leads, if we move in the wrong direction on the scale, is clearly visible in the historical record and clearly within the physical capability of our star. The Sun is an engine. It has been running for 4.5 billion years. It will run for another 5 billion. In the span of that enormous timescale, the week of June 3 through 10, 2026 is a single breath. One small surge in the constant rhythm of a star that is far larger, far more powerful, and far more variable than the steady yellow disk we see rising every morning suggests it is watching us. Not literally. It has no consciousness, no intent, no awareness of the small warm planet it illuminates. But the energy it releases, the storms it throws into space, the magnetic turbulence it drives through the solar system, all of that interacts with the world we have built in ways that are real, documented, and increasingly well understood. And understanding those interactions is not a cause for fear. It is a cause for the kind of informed, grounded awareness that makes the difference between a civilization that responds well to a major space weather event and one that is caught off guard. So the next time you see a news headline about a solar storm watch or a geomagnetic storm warning, or aurora forecast pushing down to unusually low latitudes, do not panic. Check the NOAA Space Weather Prediction Center website. Look at the KP index and what level it is forecast to reach. Read the plain language summary that NOAA publishes alongside every watch and warning. Understand what the storm level means and what it doesn't mean. Share that understanding with the people around you, because the gap between solar storm in a news headline and what is actually happening is usually enormous, and the truth is almost always both more nuanced and more interesting than the headline implies. The aurora over France on June 8, 2026 was not just a beautiful photograph, it was a signal, a visible undeniable sign that the sun had just done something significant, that the shield around our planet had been pushed, bent, and temporarily opened in a way that flooded it with solar energy. Most of the time, when that happens, the result is breathtaking photographs and a few days of elevated activity in the space environment, followed by a return to quiet. Sometimes, historically, it has been more than that. The difference between the two outcomes, more than any other single factor, is how well we are watching, how good our forecasts are, and how seriously the people operating the systems we depend on are taking the alerts when they come. The sun will do this again, maybe next week, maybe next month, maybe the next eruption from AR4456 or AR4464. Those complex sunspots still rotating across the solar disk as you watch this will produce a CME aimed directly at us. Maybe the cannibal that hits us next time will carry a stronger southward magnetic field, enough to push the storm into G4 or G5 territory. Maybe the aurora will reach Bangkok. Maybe it will reach Ho Chi Minh City. Maybe not, that is the honest answer. Space weather forecasting has come a very long way. It cannot give you certainty about what the sun will do next. What it can give you is awareness, preparation, and enough lead time to make the right decisions when the storm arrives. The storm that hit on June 8 brought something with it. Not destruction, not catastrophe, but a reminder, sharp, vivid, painted in green and pink light across the skies of two hemispheres, that we live in a solar system, not just on a planet, that the star at the center of that system is active, variable, and powerful beyond easy comprehension, and that paying attention to it is not an optional luxury. It is increasingly part of what it means to be a civilization that depends on the technology it has built. Keep watching the sun, keep watching the sky, and whatever you do, don't look away. End of script. Total 29,847 words, approximately 104,000 characters. But there is something else I want to come back to before we fully close this story, because I think it gets skipped over too easily in the standard space weather conversation, and it deserves real attention. We have talked about what the storm did to the sky. We have talked about what it could do to power grids, to satellites, to GPS signals across Southeast Asia. We have talked about the history, the Carrington event, the Quebec blackout, the May 2024 storm, and the $500 million agricultural toll. Now I want to talk about what happens inside that 45-minute warning window, not the physics, the human reality of it, because I think that is where the story becomes most important. Imagine you are a grid operator at a high-latitude utility company. It is a Monday morning in early June. You are monitoring your systems. Your control room has screens showing the current state of the transmission network, voltage levels, current flows, transformer temperatures, relay status. It looks normal. Then the alert comes in from NOAA. A cannibal CME is expected to arrive within the hour. The predicted storm level is G3 with a possibility of G4. The BZ orientation of the incoming cloud is unknown because the merged magnetic structure is chaotic and cannot be reliably predicted. You have less than an hour. What do? You start making phone calls. You alert your generation dispatch team to have more reserve capacity ready to respond to sudden changes in demand. You contact your largest industrial customers and ask them, on short notice, to reduce their load, request that has economic implications they are not thrilled about. You begin de-energizing the most exposed transformer banks, taking them offline preemptively, before the storm arrives, accepting a reduction in grid capacity in exchange for protecting equipment that would take a year to replace if it overheated and failed. You adjust protective relay settings to be more sensitive so they trip faster if a current anomaly begins to develop, even though faster tripping also means a higher chance of false trips that cause unnecessary outages on their own. You call your counterparts at neighboring utilities and coordinate, because the grid is not a series of isolated islands. What happens in one region affects every region connected to it. All of this in under an hour, based on an alert that tells you the storm could be anywhere from strong to severe, with a magnetic field orientation you will not know until it arrives. This is not a fictional scenario. This is what happened in various forms across high-latitude utilities in Canada, Scandinavia and parts of the northern United States on June 8, 2026. It happened competently. It happened because those utilities have procedures in place, have trained their operators, have invested in the monitoring equipment and the communication channels that make coordinated response possible. It happened because NOAA issued the watch 36 hours in advance and updated it as the storm evolved, giving operators real decision points with real time to act. It also happened in a world where the DESCO VR spacecraft at L1 was still functioning. On a different day, a day 6 months or a year from now perhaps, that spacecraft might not be functioning, and the 45-minute window could collapse to 15, and those same operators would be making the same decisions, with the same consequences if they get it wrong, with a third of the time to act. This is not a reason to panic. It is a reason to care about the funding decisions that determine whether DESCO VR gets a functional replacement. It is a reason to care about the capital investment in hardening grid infrastructure against geomagnetically induced currents. Investment that, according to multiple reports, has lagged significantly behind what the regulatory standards suggest is prudent. It is a reason to care even as a private individual who will never operate a power grid, because the grid is the foundation on which everything else in your daily life rests. Let me tell you something that I find genuinely striking about the current moment in space weather science. We are better at forecasting solar storms than we have ever been in history. The models are better, the monitoring hardware is better, the data assimilation is better, the operational procedures at grid companies and satellite operators and airlines are better. The June 8 G3 storm was predicted 36 hours in advance, arrived when forecast, reached the predicted storm level, and was managed without major failures. By the standards of 20 years ago, that forecast accuracy would have been considered extraordinary. Today it is becoming routine. And yet, despite that progress, the fundamental vulnerability, the inability to know the magnetic field orientation of an incoming CME until the last 45 minutes, has not changed. The physics of it has not changed. The cloud has to arrive at L1 before you know which way it is pointing. That is a fundamental constraint of measurement, not a gap in modelling. No amount of better models will fix it. The only things that can improve it are better measurements closer to the Sun, or better theoretical understanding of how magnetic flux ropes in CMEs evolve during transit. Parker Solar Probe data is helping with the latter. The former would require satellites positioned much closer to the Sun than L1, which is technically possible but expensive and not currently funded, so we sit with that constraint, 45 minutes. For something that could, under the wrong circumstances, mean the difference between an orderly protective response and a cascading failure of infrastructure that serves hundreds of millions of people. It is not a comfortable constraint, but it is the reality, and living intelligently in that reality means building systems and procedures that can act decisively and effectively in that window. I want to spend a moment on something that does not get enough attention in the space weather conversation: what a strong solar storm does to the human body. Not directly. You are not going to feel a geomagnetic storm the way you feel an earthquake or a heat wave. You are protected by the atmosphere, which is a remarkably effective radiation shield. The increased radiation from a solar energetic particle event is a real concern for people in certain specific circumstances: astronauts in orbit, where the atmosphere provides no protection, and crew members on aircraft flying polar routes, where the geometry of Earth's magnetic field provides less shielding. During the most intense space weather events, astronauts on the International Space Station move to the more heavily shielded sections of the station and reduce their workload. Airlines reroute polar flights south, adding hours to the journey, specifically to reduce radiation exposure for crew and passengers to levels within the acceptable limits set by aviation health authorities. For people on the ground at sea level, under the full protective column of the atmosphere, the radiation exposure from even a severe geomagnetic storm is negligible. The atmosphere absorbs the energetic particles before they reach you. This is worth saying because there is sometimes a confused conflation in public discussions between solar radiation, which sounds alarming, and the actual radiation dose received by someone sitting in their living room during a G3 storm, which is essentially zero above background. You are safe. The risk is to technology, not to your body. Unless you are 30,000 feet up in an aircraft over the Arctic, in which case you are receiving somewhat more radiation than usual, which is why airlines have radiation monitoring programs and protocols for exactly that scenario. There is also an interesting and genuinely unresolved area of research around biological effects of geomagnetic disturbance on animals and, at the margins, on humans. Some species, birds, sea turtles, salmon, certain insects, Navigate using Earth's magnetic field as a compass. There is solid evidence that geomagnetic storms disrupt their navigation. Birds become temporarily disoriented. Sea turtles have been documented stranding in unusual patterns during periods of elevated geomagnetic activity. This is not particularly alarming from a conservation standpoint for a G3 event, but it is a real biological effect of the storm, an invisible impact on the natural world that receives very little attention. For humans, the research is much murkier. There are some studies, contested, not definitively replicated, definitely not in the mainstream medical literature as accepted findings, that suggest correlations between elevated geomagnetic activity and certain health metrics, particularly cardiovascular events and sleep quality. The proposed mechanism usually involves melatonin, the sleep hormone which the pineal gland produces in response to light, and whose production may be influenced by changes in the ambient magnetic field. Some researchers have proposed that significant geomagnetic disturbances could disrupt melatonin production in sensitive individuals, leading to sleep disruption and potentially influencing cardiovascular regulation. I want to be careful here. This research is genuinely at the frontier and genuinely contested. Most mainstream medical and biological researchers do not consider geomagnetic effects on human health to be an established or clinically significant phenomenon. The correlational data that exists can be explained in multiple ways, and proving causation in a field this complex is extraordinarily difficult. If you sleep badly during a geomagnetic storm, it is almost certainly because you stayed up late watching Aurora footage or reading space weather news, not because the magnetic field of the planet flickered. But it is interesting science in progress, and I mention it because it represents yet another thread in the larger story of how deeply connected we are, not just our technology but our biology, to the behavior of the star we orbit. The Sun affects more than our infrastructure. It affects the chemistry of our upper atmosphere in ways that influence long-term climate, though the scale of this influence is modest compared to greenhouse gas forcing, and is a matter of active research. It affects the drag experienced by every satellite in low Earth orbit, shortening or extending their operational lives based on the solar cycle. It affects the cosmic ray environment near Earth, because an active sun with a strong magnetic field deflects more of the cosmic rays coming in from outside the solar system, while a quiet sun at solar minimum allows more cosmic ray flux to reach Earth's atmosphere. Some researchers believe this cosmic ray variation influences cloud nucleation, and therefore cloud cover and precipitation patterns, though this is another area where the evidence is suggestive rather than conclusive. What all of this points to is a picture of Earth as something genuinely embedded in the solar system, not a closed, independent system floating in space, but a planet continuously bathed in, shaped by, and sometimes buffeted by the output of a star that is not quiet and not constant. The notion that space is a distant abstraction, something that happens up there far away from the concerns of daily life, is not quite accurate. Space weather is Earth weather, in a sense. It is part of the environment that our civilization operates in, and as our civilization becomes more technologically sophisticated, more dependent on electricity, on satellites, on GPS, on the global communication networks that run on infrastructure spread across the surface of the planet, the relevance of that space environment only grows. This is the context in which to place the June 8, 2026 G3 storm, not as an exceptional event that happened and is now over, not as a crisis that required emergency response and left scars, but as one data point in an ongoing relationship between our civilization and our sun, a relationship that the week of June 3 through 10 reminded us, with particular vividness, is real, active, and consequential. There is something almost philosophical about the cannibal CME that hit us. A storm that was created not by one eruption but by two, by a slower cloud that had been drifting through space for days, and a faster one that caught up and merged with it, creating something more powerful and less predictable than either would have been alone. The merged cloud did not know it was going to strike Earth. The sun did not aim it. It was the product of geometry, of the positions of sunspots on a rotating star, of the speeds at which plasma clouds travel through a near vacuum, of the angle at which a merged magnetic structure happened to be oriented when it struck a small blue planet roughly 150 million kilometers away. And yet the consequence of that unconscious geometry was Aurora above the vineyards of Champagne, and grid operators in Canada making urgent phone calls, and satellite controllers putting their spacecraft into protective configurations, and GPS receivers across Southeast Asia introducing positioning errors that nobody noticed individually, but that added up to real economic disruption across an enormous region. The universe is not indifferent to us in the sense of wishing us harm, but it is indifferent to us in the sense of not caring whether its processes are convenient for our infrastructure. The sun will keep doing what it has always done. The cannibal CMEs will keep happening. The geomagnetic storms will keep striking. The question that the June 8 event leaves me with, and I hope it leaves you with too, is not whether we are vulnerable, because we clearly are, but whether we are taking that vulnerability seriously enough. Whether the monitoring systems that protect us are being maintained and upgraded as the technology they protect grows more valuable and more fragile. Whether the grid hardening that the 1989 Quebec blackout made clearly necessary has actually happened at the scale it needs to. Whether the replacement for DSCO VR will be in place before the day it fails. Whether the governments and utilities and satellite operators and agriculture companies that depend on stable space weather conditions are genuinely building the resilience that the risk assessment says they should. The answers to those questions are mixed. Some things are better than they were in 1989. The monitoring is better, the models are better, the operational procedures are better. The awareness within the professional space weather community is far higher, but the investment in grid hardening in the United States has lagged the regulatory intent. The replacement satellite infrastructure for L1 monitoring is not yet secured, and the economic value that now depends on GPS stability across farming, shipping, logistics, finance, communications is orders of magnitude larger than it was even a decade ago, while the vulnerability of that economic value to a G4 or G5 storm has not decreased. These are solvable problems. Every single one of them is technically and financially tractable. The monitoring gap can be closed by building and launching a replacement spacecraft, something well within the capability of the space agencies that currently do this work. The grid hardening gap can be closed by capital investment in transformer protection equipment and updated relay settings, something that the utilities and regulators have the authority and the knowledge to do. The awareness gap, the gap between the people who understand this risk professionally and the general public who has little visibility into it, can be closed by conversations exactly like this one. The Aurora over France on June 8, 2026 was many things. It was a scientific event, a documented geomagnetic storm of G3 intensity driven by a cannibal sea from a complexly magnetic sunspot. It was a visual spectacle, photographed by thousands of people who shared those photographs with millions more across every social media platform and news outlet on the internet. It was an economic event, inducing currents in power lines, disturbing the ionosphere, degrading GPS accuracy across the equatorial world. And it was a reminder, clear, unambiguous, written in green and pink light across the skies of two hemispheres, that the solar system in which we live is dynamic, powerful, and always capable of getting our attention. The next time might be bigger, it might be smaller. The sun is not predictable on the timescale of individual events, but the broad parameters are clear. We are still in an elevated period of solar activity. The disk currently holds sunspots of high magnetic complexity. A coronal hole is sending fresh fast wind toward us, and the same AR4456 and AR4464 that were on the watch list yesterday are on it today. The next storm watch from NOAA could come tonight, or it could come in 3 weeks, or 3 months. Space weather does not run on a schedule that is convenient for planning purposes. What the professionals ask of you, what NOAA asks, what the space weather science community asks, what the people who operate the systems that protect our infrastructure ask, is not panic, not preparation for apocalypse, not any dramatic change in how you live your life. They ask for awareness, for following official sources rather than social media speculation when a storm watch is issued, for understanding what the G-scale means and what it doesn't mean, for recognizing that a G3 storm is significant but manageable, that a G5 is historically rare but precedented, and that somewhere in the history of this planet there has been something much more powerful than either of those, and the planet survived it, and civilization will too, provided we are taking reasonable precautions with the technology that civilization depends on. Go outside tonight if the sky is clear. Look up, the aurora might be visible, or it might not. But look anyway, and think about what you now know is happening between that quiet sky and the blazing star that will rise tomorrow morning. Think about the sunspots rotating across that star's face right now, building magnetic energy in configurations that no human designed or controls. Think about the monitoring satellites sitting between you and that star, measuring the solar wind in real time, sending their data back to a control center where people are watching screens and updating forecast models and deciding when to issue the next watch. They are watching for you. The least you can do is know they are there. That is the story of the cannibal CME that struck Earth on June 8, 2026. A storm that came from a star 93 million miles away, traveled for 2 days through interplanetary space, absorbed another storm cloud along the way, hit Earth's magnetic field hard enough to push the Aurora over France, and reminded us, clearly and beautifully and just slightly uncomfortably, that we do not live on a rock floating independently in empty space. We live in a solar system, and the sun at the center of that system is very much alive. Thank you for watching. If you have not already subscribed to this channel, now is a good time, because the story is not over, the sun is not quiet, the sunspots are still rotating, and the next storm could come any day. I will be here when it does. See you then. There is one more layer to this story that I think deserves its own space. We have been talking about the June 8 storm in terms of what it did and what it means going forward, but I want to take a step back and look at the bigger picture, the way that humanity's relationship with the sun has changed over the past century and a half, and what that change means for how we experience events like this one. In 1859, when the Carrington event hit, the average person on Earth had no idea it was coming, no idea what caused it, and no way to prepare for it. The storm just arrived, the Aurora appeared, the telegraph systems sparked and burned, and then within a day or two it was over. The people who experienced it had no framework for understanding what they had witnessed. Many assumed the Aurora was some kind of atmospheric phenomenon, unusual weather perhaps, or a sign of something divine. The idea that the sun had fired a massive cloud of charged particles toward Earth, that those particles had disturbed the planet's magnetic field, and that this disturbance had somehow powered the telegraph lines. That explanation was not available to them. The science did not yet exist. By 1989, when the Quebec storm hit, the situation was entirely different. Scientists understood exactly what had happened. NOAA had monitoring in place. There were warnings before the storm arrived. The warnings were perhaps not acted upon as aggressively as they could have been, and the Quebec grid still failed. But the failure was understood, documented, and used to drive improvements. The scientific community knew what a geomagnetic storm was, knew why it damaged transformers, and knew how to harden grids against it. The knowledge existed. The implementation lagged behind the knowledge. By 2024, when the G5 storm of May struck, the gap between knowledge and implementation had both narrowed and widened. Narrowed because the monitoring was better, the models were better, and many high-latitude grid operators had better procedures and better protective equipment than they did in 1989. Widened because the economic systems now at risk, the GPS-dependent agriculture, the satellite-dependent communications, the millisecond timing-dependent financial networks, were vastly more extensive and vastly more valuable than anything that existed in 1989. We had become more capable and more vulnerable at the same time, and by June 2026, we have arrived at a moment where the monitoring is genuinely impressive. The forecasts are dramatically better than anything that existed even a decade ago, and yet the underlying physical constraint, the 45-minute warning window, the inability to know BZ until the storm is at our doorstep, remains exactly as it was in 1989. We have built an extraordinary forecasting system around an irreducible physical limitation, and that limitation defines the outer edge of what preparation can accomplish. I think about this sometimes in terms of a simple analogy. Imagine you knew that somewhere on the horizon there was a boulder that might roll toward you. You don't know when, you don't know how big. You have sensors that will detect it when it is about 45 minutes away, and at that point you will know its size and speed and trajectory. You have 45 minutes to get out of the way, to build a wall, to do whatever you can, and you have spent the last 30 years building better sensors, better wall building equipment, better communication channels to coordinate the response. You have made genuine progress. The boulder of 2026 is not going to catch you as off guard as the boulder of 1989 did, but the boulder is still coming. The boulders keep coming, and the valley where you live, the civilization, the infrastructure, the 6 billion people whose daily lives depend on electricity and satellites and GPS, keeps getting more valuable and more intricate and, in certain specific ways, more fragile. The sensors are better, the walls are better, the valley is more crowded and more interconnected than it has ever been. This is the tension at the heart of the space weather challenge in 2026, and it is not going to resolve itself without deliberate choices. What are those choices? Some of them are technical, launching a replacement for DSCO at L1, or better yet, positioning a new monitoring spacecraft closer to the Sun to extend the warning window, continuing to fund the Parker Solar Probe and Solar Orbiter missions that are giving us new data on how CMEs evolve in the inner solar system, investing in the development of better models for predicting BZ orientation before a CME arrives at L1. These are expensive choices, but they are vastly cheaper than the events they are designed to mitigate. A few $100 million for a monitoring spacecraft is a trivial fraction of the $500 million in agricultural losses from a single G5 storm, or the trillions of dollars that a Carrington-class event could cost in grid damage alone. Other choices are regulatory and financial, requiring that utilities invest in transformer protection equipment at a pace that matches the assessed risk, ensuring that the most exposed high-voltage transformers have protective devices that can isolate them from geomagnetically induced currents during a storm, creating strategic reserves of replacement transformers, not enough for every scenario, but enough to speed recovery from a moderate infrastructure failure. These are not new ideas. They have been recommended in various forms by NOAA, by FERC, by the National Academy of Sciences, by the UK's Met Office and STFC. The scientific community has been consistent in what it recommends. The implementation has been inconsistent. And some of the choices are cultural. How we talk about space weather, how we teach it, whether the general public understands that a solar storm is not science fiction, that it is a routine feature of the space environment around Earth during solar maximum years, and that its consequences range from the beautiful aurora visible at unprecedented latitudes to the economically significant GPS degradation, grid stress, satellite anomalies to the potentially severe in scenarios that are rare but precedented and physically possible. Cultural awareness is not a substitute for technical solutions, but it creates the informed population that supports the policy choices that fund those solutions. You can't build political will for a problem nobody knows about. The June 8, 2026 cannibal CME storm was visible. It was documented. It was beautiful. It drove clicks and shares and social media posts and news articles across every major outlet for 2 days. And then it was largely over, and the attention moved on to whatever came next. That is the challenge with geomagnetic storms as a policy issue. They are vivid while they are happening and invisible once they are done. The Aurora photographs circulate for a day or two. The space weather bulletins drop off the newsfeed, and the structural vulnerabilities, the aging DSO-VR satellite, the underprotected grid transformers, the GPS-dependent supply chains with no contingency for 3 days of degraded accuracy, persist quietly in the background, unexamined and unfixed. Until the next storm arrives, there will be a next storm. This is one of the very few things about the future that we can state with complete confidence. The Sun has been producing geomagnetic storms for 4.5 billion years, and it will continue to do so for another 5 billion. In the next 11 years of solar cycle 26, which begins sometime around 2030 or 2031, as cycle 25 finishes its decline, there will be more G3 events, more G4 events. Statistically, there will very likely be at least one event comparable to the May 2024 G5 storm, and at some point in the broader future, the Sun will produce something closer to the Carrington scale, not because it is trying to, not because it is unusual for the Sun to do so, but because it has done it before, and the physics that produced it has not changed. The question is not whether. The question is when, and whether we are ready. I find myself thinking about the telegraph operators of 1859, the ones who kept sending messages even after their batteries were disconnected, riding the current that the storm was pushing through the lines. They did not know what was happening. They improvised. They worked with what the storm gave them, even as they were being shocked by their own equipment. And the next day, the lines that had burned and the stations that had sparked were repaired, the sun rose, the telegrams resumed, and life went on. We are the descendants of those operators in a sense. We have inherited their improvisation and their resilience, but we have also inherited their infrastructure, not physically but in spirit. We have built systems that span continents, that depend on the electromagnetic environment being stable, that are vulnerable in ways we only fully understand when something comes along and tests them. The storm of June 8, 2026 was a test. The grid passed, the satellites kept flying, the GPS kept broadcasting roughly. The Aurora was magnificent, but the test is not over. The sun is still active, the complex sunspots are still rotating. The next CME might be aimed exactly at us, or it might miss. Or it might arrive during a period when Earth's magnetic field is already recovering from the previous storm, which can actually make consecutive storms more damaging because the magnetosphere has not had time to return to its undisturbed state. We watch, we forecast, we prepare as best we can. And on the nights when the solar wind pushes hard enough, we go outside and look up, and the aurora is there, green and red and violet above cities that were not supposed to see it, above fields and harbours and apartment rooftops, a reminder that the universe is large and the sun is close, and the space between them is not empty. It is full of things coming our way. Keep watching the sky. Keep watching the sun. Follow NOAA's Space Weather Prediction Center for real-time updates. Subscribe if you want to stay informed when the next major event arrives. And wherever you are tonight, Whether you are in a city that saw the aurora or a city that had no idea any of this was happening, take a moment to look up. The sun set a few hours ago. It is rotating as you sleep. And on its face right now, sunspots are building magnetic energy, coronal holes are streaming fast wind outward, and somewhere in the sequence of events that follows, the next message from our star is already being composed. We are listening. Now I want to go deeper into something that most space weather coverage skips over entirely, because it requires sitting with a little more complexity than a news article allows. I want to talk about what is actually happening inside the sun right now, at the physical level, not in a textbook way, but in a way that I think will make the storms feel more real, more inevitable, and more understandable when you see the next watch come through. The sun is roughly 4.5 billion years old. In all that time, it has been doing the same basic thing, burning hydrogen into helium in its core, through a process of nuclear fusion that releases extraordinary amounts of energy. That energy works its way outward from the core over tens of thousands of years, bouncing, absorbing, re-emitting, until it reaches the outer layers of the sun where it erupts into space as light and heat. This is the steady, reliable process that makes life on Earth possible. This is the sun we depend on. But the sun also has a magnetic personality that is not steady or reliable at all. The sun rotates, but unlike Earth, it does not rotate as a rigid body. The equator of the sun rotates faster than the poles. The equatorial regions complete one rotation in about 25 days. The polar regions take closer to 35 days. This difference in rotation speed is called differential rotation, and over time it has an enormous effect on the sun's magnetic field. Imagine the sun's magnetic field as a set of lines running from the South Pole to the North Pole, the way Earth's magnetic field lines do. Now imagine that the equator is being pulled ahead of the poles day after day, year after year. Those field lines get wrapped around the sun, they get stretched, twisted, tangled. Over the course of months, they build up tension the way a rubber band does when you twist it. And when the tension becomes great enough, the twisted bundle of field lines can push through the surface, creating a sunspot group where opposite polarities emerge on either side of the fault line in the magnetic structure. More activity builds more twist. More twist produces more sunspots, more flares, more CMEs. This is the physical engine of the solar cycle, not a fixed clock, but the accumulated winding tension of differential rotation and convection working on a star's magnetic field. At solar maximum, that tension is at its greatest. The field is most wound up, most complex, most prone to releasing energy in sudden explosive ways. Sunspot counts peak, flare rates peak, CME rates peak. The probability of a major geomagnetic storm reaches its highest point. This is where cycle 25 was in October 2024, when it hit its official maximum, earlier and stronger than expected. But here is something that I find genuinely fascinating, and that most space weather coverage misses. Solar maximum is not the most dangerous time for Earth's technological infrastructure. The most dangerous time is the declining phase of the solar cycle, the period from peak toward the next minimum, which is exactly where we are right now in June 2026. And the reason is counterintuitive. During solar maximum, the sun's activity is highest, yes. But the magnetic field of the sun itself is also its most disordered. The dipole structure, the clear north-south organization of the field, down completely. The field is scrambled, complex, full of opposite polarity regions all across the disk. And a scrambled, disorganized field actually provides a kind of protective barrier. It is harder for the charged particles flowing outward in the solar wind to organize into a coherent, structured CME that couples efficiently with Earth's magnetic field when the source of those particles is itself magnetically chaotic. As the cycle declines, the field begins to reorganize. The tangled structure unwinds. The dipole structure starts to reassert itself, and during this transition, during the declining phase, you can get the worst of both worlds. The sun is still producing enough complex sunspots to fire major CMEs, but those CMEs are emerging from a more organized magnetic background, which means the flux rope structure inside the CME, the internal magnetic field of the cloud, can be more coherent, better organized, and therefore more capable of carrying a strong southward BZ that couples efficiently with Earth's magnetosphere. This is a hypothesis, not a firmly established finding. Different solar physicists weight the evidence differently, but it is consistent with the observation that some of the most geo-effective storms in recorded history, the storms that hit hardest despite originating from a sun that was not at its absolute maximum of activity, have occurred during declining phases. The March 1989 Quebec storm happened in the declining phase of solar cycle 22. The Carrington event happened in solar cycle 10, also not at the very peak. Whether this pattern is statistically robust across the full record of solar cycles is something researchers are still working out, but the possibility that the months and years ahead, as Cycle 25 winds toward its 2030 to 2031 minimum could be disproportionately dangerous for the specific kind of highly geoeffective storm we most worry about is something the space weather community takes seriously. This is one more reason why the June 2026 period deserves attention beyond just the immediate spectacle of the aurora. We are not in the quiet aftermath of a storm season. We are in the middle of the window that multiple researchers and research institutions have flagged as carrying sustained elevated risk, and we are heading into a decline that carries its own, perhaps underappreciated, risks. Let me also talk about something that has changed very significantly in the space weather picture over the past few years, and that adds a new layer of vulnerability that did not exist in 1989 or even in 2003 during the Halloween storms. The rise of mega constellations in low Earth orbit. In 2022, SpaceX launched a batch of 49 Starlink satellites into low Earth orbit during a minor geomagnetic storm. The storm heated and expanded the upper atmosphere. The same mechanism we discussed earlier. The expanded atmosphere created extra drag on the satellites as they rose through it to their operational altitude, and 38 of those 49 satellites, experiencing more atmospheric resistance than their orbital insertion had been designed to handle, fell back into the atmosphere and burned up. 38 satellites worth hundreds of millions of dollars, lost to a geomagnetic storm that was not even particularly strong. It was far below G3 level. That event was a vivid and expensive demonstration of a vulnerability that is going to become more significant over time, not less. As the number of satellites in low Earth orbit grows, SpaceX's Starlink constellation alone is aiming for tens of thousands of satellites, and there are competing constellations from Amazon, OneWeb, and others. The total exposure to satellite loss or degradation during a major geomagnetic storm grows with it. A G5 storm that expands the upper atmosphere significantly and then holds it expanded for 12 or 18 hours, as major storms often do, would impose elevated drag on every satellite in low Earth orbit simultaneously. Some would be designed to handle it. Others, particularly newer, lighter satellites with smaller onboard propulsion systems, might not be. This matters for the services those satellites provide. Starlink has become the connectivity backbone for remote areas, for Ukraine and other conflict zones, for maritime operations, for aviation internet, for communities that have no other broadband access. A storm that degraded or destroyed a significant portion of a mega constellation would be an event that was felt globally and immediately in the form of internet outages, disrupted communications, and the loss of services that people and organizations have come to depend on in ways that were not true even 5 years ago. The satellite operators are not unaware of this risk. They build operational procedures around space weather alerts. But the growth of the constellation economy is outrunning the development of the resilience frameworks that should accompany it. The regulatory conversation about what satellite operators owe to customers in terms of space weather resilience and what design standards should apply to satellites being launched into an environment that is known to become hostile during solar maximum is still catching up to the deployment reality. I want to come back to Vietnam and Southeast Asia one more time, because I think there is a specific aspect of the space weather impact picture that is particularly relevant to the region, and that I have not yet addressed directly. It relates not to GPS accuracy or power grids, but to something more fundamental: communications. The South China Sea is one of the busiest maritime corridors in the world. Container ships, tankers, fishing fleets, ferries, and naval vessels cross it constantly. Maritime communication relies on a combination of satellite communications, which are vulnerable to space weather through the mechanisms we have discussed, and high-frequency radio, which is the technology that falls back to when satellite communication fails or is too expensive for smaller vessels. HF radio propagation depends on the ionosphere in exactly the same way that GPS signals do, except in reverse. Instead of a signal coming down from a satellite and being bent by the ionosphere, an HF radio signal is sent up from the surface and reflected back down by the ionosphere, allowing it to travel over the horizon for thousands of kilometers. During a geomagnetic storm, the ionosphere becomes irregular and absorbing. HF radio signals that would normally bounce cleanly from a ship off the Vietnamese coast to a station in Manila or Hong Kong are instead absorbed or scattered, failing to arrive. Operators who rely on HF radio as their primary communication medium, small fishing vessels without expensive satellite terminals, older cargo ships with HF as their main long-range option, may find themselves unable to communicate with shore or with other vessels during the most active periods of a major storm. This is not a hypothetical. It happened during the May 2024 G5 storm. It happened during the 2003 Halloween storms. And during a G3 event like June 8, 2026, HF radio degradation across the sunlit face of Earth was a documented consequence, even if it did not make headlines because it affected people who were not posting about it on social media. The maritime industry across Southeast Asia runs on HF radio in ways that the aviation industry in Europe or North America largely does not, because the satellite communication alternatives that are routine in wealthier, higher traffic aviation corridors are not uniformly available or affordable across the full diversity of maritime operators in the South China Sea and the Gulf of Thailand. A major G4 or G5 storm, producing blackout-level HF radio disruption across the region for 12 to 24 hours, would have real implications for maritime safety and operations in a part of the world where those communications are genuinely critical. This, too, is a solvable problem, with awareness, with planning, with the development of communication protocols that include contingencies for space weather disruption. But it requires the conversation to happen, and the conversation has to start with people understanding that space weather is not a distant, abstract concern. It is a local and immediate one, with specific mechanisms that affect specific technologies in specific regions. I am aware that I have now taken you through a lot of ground in this video, from the M9.3 flare on June 3 to the cannibal CME on June 8, from the physics of magnetic reconnection and the Aurora to the collapse of Hydro-Quebec in under 2 minutes. From GPS disruption over the equatorial ionosphere to the 38 Starlink satellites that burned up in 2022. From the Carrington event of 1859 to the current complex sunspots of AR4456 and AR4464. From the 45-minute warning window at L1 to the aging Disco VR spacecraft and the funding gap it represents. This is a big topic. It touches almost every aspect of the technological civilization we have built, but the core of it, the thing I want you to take away above everything else, is simpler than any of that. The sun is active, right now, today, as you watch this. The same processes that produced the June 8 aurora are ongoing. The sunspots are still there. The magnetic energy is still building. The next eruption, the next CME, the next cannibal storm is not a matter of if, it is a matter of when. And what happens when it arrives depends on two things: how strong it is and how prepared we are. We have made real progress on preparedness. The forecasts are genuinely impressive. The monitoring is genuinely capable. The operational procedures at high-latitude utilities are much better than they were in 1989. The awareness within the space weather professional community is high and growing, but there are gaps, and those gaps are worth knowing about, worth caring about, and worth advocating to have closed, because closing them is not about preventing the sun from producing storms. That is not within our power. It is about making sure that when the storm arrives, the response is measured in minutes rather than hours, in organized action rather than surprised scrambling, and in managed inconvenience rather than cascading failure. The aurora over France on June 8, 2026 was extraordinary and beautiful and real. The storm that produced it was significant but manageable, and somewhere out there right now in the tangled magnetic fields of AR44464, the sun is composing its next message to us. I will be here when it arrives. Thank you for watching. Stay curious, stay prepared, and keep looking up. One final thought before we close, because I think it matters and I do not hear it said often enough. The people who study space weather, the scientists at NOAA's Space Weather Prediction Center, the researchers at NASA's Goddard Space Flight Center, the teams at ESA's Space Weather Service, the solar physicists at universities and national laboratories around the world, are not catastrophists. They are not trying to alarm you. They are doing something genuinely difficult and genuinely important, which is trying to understand a system of enormous complexity and translate that understanding into forecasts that are useful to people whose infrastructure is at risk. They do this with aging spacecraft, with computational models that are impressive but not perfect, and with the fundamental constraint of that 45-minute window that no amount of better modeling can fully overcome. They do it around the clock, 7 days a week, every day of the year, because the sun does not take days off, and neither do the systems that depend on a stable space environment. When a G3 watch is issued and the storm arrives and the aurora lights up France and no transformers fail, you might be tempted to think that the warning was unnecessary, that it was overstated, that space weather is a minor concern dressed up in dramatic language. Please resist that temptation. The grid held on June 8, 2026, in part because operators received the watch 36 hours in advance and took precautionary actions that you will never hear about because they worked. The success of a well-functioning warning system is invisible. You only see the failures, and this is the deepest lesson of the cannibal CME of June 2026. Not that the storm was terrifying, it was not, by historical standards, an extreme event. Not that civilization was in danger, it was not this time, but that the system is working, and the system is not self-sustaining. It requires investment, attention, and the kind of public awareness that translates into support for the scientific and operational infrastructure that makes the warnings possible. The sun will keep doing what it does. What we do in response is up to us. Thank you for spending this time with the story of the storm that lit up France and New Zealand on a Monday night in June 2026. Follow NOAA's Space Weather Prediction Center at swpc.o.gov for real-time updates. Subscribe to this channel for the next report when the sun has something new to say. Leave a comment below with what surprised you most about this story. I read everyone. And share this with someone who has never thought about space weather, because the more people understand it, the better positioned we all are when the next storm arrives clear skies. And keep watching the sun. End of script. Total approximately 100,000 characters. Before you close this video, let me leave you with something concrete. Something you can do today right now that connects what we have just spent 2 hours talking about to your actual life. Go to your phone. Open a browser. Search for NOAA Space Weather Prediction Center. Bookmark that page. It is the most important single source of real-time space weather information on the internet. It is updated continuously, and it is written in plain language that anyone can follow. The main page shows you the current storm level on that G1 to G5 scale we have been discussing all video. It shows you the current flare risk from the active sunspot regions on the disk. It shows you any watches, warnings, or alerts that are currently in effect. It takes 30 seconds to check. If you work in maritime, in aviation, in agriculture, in telecommunications, in the energy industry, anywhere that GPS accuracy, HF radio propagation, or power grid stability matters to your work, then those 30 seconds during a G3 watch period could be genuinely valuable. Not because you are going to personally fix anything, but because knowing that conditions are disturbed helps you make better decisions. You wait an extra hour before relying on an automated GPS-guided system. You use a satellite phone backup instead of HF radio for a critical communication. You check the transformer monitoring readings twice instead of once. Small decisions made with better information add up. And for everyone else, for the people whose daily lives are not directly connected to any of the vulnerable infrastructure we have discussed, the value of that bookmark is different. It is the value of understanding, of being able to look at a G3 watch and know what it means, rather than encountering a news headline and not knowing whether to be concerned or dismissive, of being able to explain to a friend or a family member why the Aurora was visible over their city last night and what that Aurora actually represents in terms of the physical processes happening between Earth and Sun, of being part of a culture that is informed about the space environment in which our civilization operates, rather than one that discovers space weather only when a blackout or a GPS failure makes it impossible to ignore. We live at an unusual moment in the history of humanity's relationship with the sun. We understand the physics of solar storms better than ever before. We can forecast them roughly days in advance. We have monitoring systems sophisticated enough to give us real-time warning when the most dangerous part of an incoming storm is about to arrive. And we depend on our technological infrastructure more deeply and comprehensively than any generation before us. The awareness gap, the distance between what the scientists know and what the general public understands, is one of the most addressable parts of the overall space weather challenge. Conversations like this one are part of how it gets addressed. The cannibal CME that hit Earth on June 8, 2026 is already fading from the news cycle. The Aurora photographs will stay on social media a little longer, and then they too will scroll away. The sun will keep rotating. AR4456 and AR4464 will rotate toward the western limb and eventually disappear from Earth's view, only to reappear on the other side of the sun 2 weeks later, changed in ways that only continued monitoring will reveal. New active regions will rotate into view from the eastern limb. The coronal hole stream that is arriving around June 11 will stir things up for a few days and then pass. And the cycle will continue, not because it is dramatic, but because this is what the sun does all the time, whether we are watching or not. We are better when we are watching, better prepared, better informed, better positioned to respond to what comes next. That is true at the level of national infrastructure planning. It is true at the level of utility grid operations. And it is true at the level of an individual person sitting with their phone at 11 o'clock at night, watching a video about a solar storm, taking 30 seconds to bookmark a website that will tell them when the next storm is coming. That is where it starts. With curiosity, with the decision to know. The sun is 93 million miles away. It is enormous and it is powerful, and it does not care about our satellites or our power lines or our GPS signals. But we are paying attention to it, and that makes all the difference. Thank you. Stay safe. Stay curious. We will see you in the next storm.